Welcome to the next lecture in this series on fundamentals of smart systems. In this particular module, we are introducing process control in Simulink. Our first lecture in this module is going to be an introduction to feedback control. So we're going to be talking about process automation and some of the fundamentals of how you automate a process intelligently. I'm going to start by teaching with an example that hopefully most of you are familiar with. So that example is driving a car. So when you're driving your car, one variable that hopefully is very important to each of you is your speed or your velocity. And the primary thing that you would do to regulate your speed or your velocity would be pushing the gas in or out more. And what's physically happening inside the car is that when you push the gas pedal, you're opening the throttle valve or the fuel flow valve in your car, and then when you're letting off of the gas pedal, that valve is closing. So this happens. This is called open loop or an open loop system, a system that is not automatically controlled. So basically, you're pushing the gas pedal, and then your velocity is whatever it is. As a human, you're sort of acting as a human controller, where hopefully you are maintaining a steady position on the gas pedal and the fuel valve, and then your car is going at the speed that you want, but you would make adjustments in real time. But physically, this is an open loop system without automatic control. Important elements of how this works is you would use the actuator. So in process control language, an actuator is the piece of physical equipment that is actually making the change to your system. In this case, it would be the gas pedal, which again is changing that fuel flow valve. If you want to be aware of the overall state of your system, like how fast you're going, you need to have a sensor that is measuring that particular variable. In this case, your velocity, which would be measured by a speedometer. And there are certainly a lot of other influencing factors that can affect how fast you're going. So these could be different environmental conditions like the wind speed. If the wind is a tailwind or a headwind, that's going to impact your speed. The different terrain is certainly huge, whether you're going up a hill or down a hill and what the slope of that terrain might be. Other things like changing engine performance over time or vehicle weight, those might also be environmental conditions that you can't control directly, at least not when you're driving your car, but that still impact critical variables like your velocity. If you wanted to regulate that velocity, many of you are hopefully familiar with the concept of cruise control. So this is a great example to teach about how process automation or process control work. So let's say we want to be able to better regulate our car's velocity. Like if we're going up a hill, we want the car itself to automatically keep you at your desired velocity despite these changing environmental conditions. So I'm going to walk you through a diagram for how process control with feedback control typically works. So in this particular example, we're going to call our car the process. So we can change things in the process like the inputs, like the fuel valve position, and then that's going to impact our output. So in this case, the output variable that we really care about is the velocity. So this is something we're going to want to pay close attention to and make sure that we're not driving dangerously fast and that we're staying within the speed limit, and also that we're not driving too slow and slowing down traffic or making us late for wherever we're going. Inputs to this particular process might include certainly the fuel valve position. So this is our independent variable, also known as a decision variable or a manipulated variable. Basically, without cruise control, this is the thing that we're actually physically changing in the car to get some desired output, which would be our velocity. Those environmental variables like wind speed and terrain slope, we might call those disturbance variables. Those can disturb our process. They can affect our velocity, for example, but we have no real control over them. If you want to control something, you have to be able to measure that thing. So every control system needs a sensor or a way to measure the thing that you're trying to control. So in this case, that would be a speedometer. or we might also call that in process control language a velocity transmitter. So this is the thing that is relaying this important information about velocity in real time to our controller. So these dashed lines represent a flow of information or a signal. So taking that velocity transmitter measurement, or VT, we would send that information to some kind of a computer that can run an algorithm within our vehicle. So I've called that here the cruise control computer. In process control language, we might call that the velocity controller, or VC. So this is running an algorithm, which I'll cover how this algorithm works in the next video lecture. A critical piece of that is going to be we need to tell our car what is the desired velocity, or this would also be known as the set point, or SP, in process control language. So this computer is going to run an algorithm based on the present and past information that it has received from our velocity transmitter. It's going to run this algorithm, and it's going to recommend a desired fuel valve position. So our velocity controller, or VC, is going to tell our fuel valve position what position it needs to be, what position the fuel valve needs to be in to give us the desired velocity. So you can see this flow of information makes a loop, and so we'll call this a closed loop control application. Once we turn the cruise control in our car, close this loop, and let the car itself regulate our velocity using our actuator to control our car. So this actuator is process control language, but also the control valve is also language here. So this signal here from our computer is going to tell this valve how much to open or close so that we hit the desired velocity, or our set point. All right, so for a practical example, if we're driving along in our car and let's say we do hit that hill, what we would be tracking would be like our velocity. So our velocity, if we're cruising along, once we hit that hill, our velocity is going to go down, and our car would decelerate. So we don't want that to happen. We want to try and maintain a steady velocity as much as we can. So we would want our controller to influence the fuel valve position here, and we'd want to tell it to, it would use our sensor, or our velocity transmitter, relay that information to our cruise control computer, or our controller, and it would say, okay, open the fuel flow valve. And so it would open that valve a little bit more, send more fuel to the car, and we might have this steady state value eventually with a higher fuel consumption. What we might see in practice here is that our velocity actually dips down a little bit because we have encountered the hill. But once that information gets through our feedback system, it goes into our sensor, or our velocity transmitter, is processed in the velocity controller, and then that is sent to our fuel valve. We might see that this disturbance does cause our velocity to drop a little bit, but then ultimately it brings it back up to our desired velocity. So in practice, this is sort of how the cruise control in your car works. I just wanted to make a point here and review some of the language that we've introduced. So without automatic control, we would be operating in open loop, meaning that we might make changes to the fuel valve position, but we don't have a great way of actually controlling what that velocity is going to be. If we close the loop and have an automatic control system in place, what that actually does is it switches our independent variable, or the thing that we are deciding. So without cruise control, we are deciding what the fuel valve position should be with our brain and then with our foot. So that's our independent variable. When we enable cruise control, we are switching our independent variable. So now we're no longer directly setting what the fuel valve position should be. Now we are telling our car and our cruise control computer what our desired velocity is, or we're giving it that set point. So that becomes our independent variable. Our actual velocity, if we have a good controller, will ultimately become the same as our desired velocity, but this would still be a dependent variable We'd call this a controlled variable, or a CV, this is the thing we're trying to control so that it reaches our desired set point. That fuel valve position now becomes a dependent variable, so that's no longer something we're directly controlling. In control terminology, we might call that a manipulated variable, or an MV. The actuator would still be the same. It would still be the fuel flow valve. That's the thing that is ultimately changing, that changes the performance of our system. And we would still have the sensor being our speedometer. We might also call that a velocity transmitter. And then our environmental conditions, we could call those disturbance variables, or those are things that are out of our control, but that still dramatically impact the performance of our system. So just a quick review, to look at this open loop process, we would be directly setting the fuel valve position, and then you're sort of just getting whatever velocity you get. So notice this is called an open loop process, and this might make more sense when you see the closed loop process again. So a closed loop process is we are taking our controlled variable, in this case our velocity, measuring it, running an algorithm on a controller to try and fix it, or try and make it match our desired velocity or our set point. And then this velocity controller ultimately will set our fuel valve position to hopefully make our desired velocity equal to our velocity. So you can just see schematically we have now made a closed loop. And so when you put a process into automatic feedback control, you are closing the loop. Stay tuned for the next video lecture, where I'm going to start getting into what is the algorithm going on inside this velocity controller. How does that work? So hopefully I'll explain that very clearly, and you'll know exactly what's going on from an algorithmic point of view.